Chapter 7, Similarity and Transformations. Let's look at what we will learn in this unit first. In this unit, we will learn how to draw and interpret scale diagrams. We will also learn how to apply properties of similar polygons to solve problems. We will need to know how to identify and describe line symmetry and the rotational symmetry. The similarity and the transformations are important in our real life because we can see them very often around us. Architects, engineers, and designers and surveyors use similarity and scale diagrams routinely in their work. Symmetry can be seen in art and nature. If we can develop a good understanding of symmetry, it can help us to appreciate and find out more about our world and to create works of art. Today, we will look at 7.1, scale diagrams and enlargements first. What is a scale diagram? What is an enlargement? On this screen, I have two pictures right now. Let's look at how are these two pictures alike? How are they different? I will see the left side picture is smaller than the right side. Or we can see the right side one is larger than the left side. And they have exactly the same shapes of these two characters, but they just have different sizes. If I call the left side the original diagram, I will call this right side, which is an enlargement of the left side one, the scaled diagram or the scaled image. What is a scale diagram? Let's look at its mathematical definition. A diagram that is enlargement or a reduction of another diagram is called a scale diagram. Let's look at two mosquito pictures. This one is smaller than this one. We say this one is the reduction of the right side image. The right side is larger than the left side. We can see the right side is the enlargement of the left side image. To compare the matching lengths in the scale diagram and in the original diagram, we can calculate the scale factor. Here is the scale factor formula. We can see the scale factor is a ratio. It equals the ratio of the length on scale diagram to the length on original diagram. To calculate the scale factor, the units of length in this ratio must be the same. If the top is in centimeters, the bottom has to be in centimeters as well. Matching lengths on the original diagram and the scale diagram are called corresponding lengths. This is a very important term we will use very often in similar polygons. When pairs of corresponding lengths have the same scale factor, we see that the corresponding lengths are proportional. So right now, we will use some examples to help us understand those concepts better. Let's look at example 1. I have two F images. This F image is the original diagram. This one is the enlargement of the original diagram. So this one is called the scale diagram. Let's determine the scale factor for this scale diagram. Find the corresponding lengths to calculate a scale factor. So use the scale factor formula. I will look at the length of vertical segment on the scale diagram, which is here. This one is 5 centimeters. So I will write out 5 centimeters on the top in the fraction. The bottom is the length of vertical segment on the original diagram. So its corresponding length is here. I will write out 2 centimeters. 5 centimeters, 2 centimeters. It will be equal to 5/2. If I want to change this one to the decimal, that's fine as well. You can use a decimal to represent the scale factor because this decimal means 2.5/1. You can omit the 1 in the denominator. So let's find the scale factor for two horizontal line segments. Length of a horizontal segment on the scale diagram, which is 2.5 centimeters. I put a 2.5 centimeters here. Length of a horizontal segment on the original diagram, its corresponding length is here, which is 1 centimeter. I put it in the denominator. 2.5 centimeters over 1 centimeter equals 2.5 again. So these two ratios are the same. So each length on the original diagram is multiplied by 2.5, which is the scale factor, to get to the matching length on the scale diagram. Example 2. Using corresponding lengths to determine the scale factor. The actual length of the mosquito is 12 millimeters. The drawing of the mosquito is 4.5 centimeters. So right now in the drawing, this one is longer than its actual length. Find the scale factor. If I want to find the scale factor, these two lengths must have the same units. So I will change 4.5 centimeters to meters, because if I change centimeters to millimeters, it will be easier than changing millimeters to centimeters. So 4.5 centimeters to millimeters, I need to multiply by 10. So the length in the scale diagram is 45 millimeters. When I need to look for the scale factor, so the length on scale diagram is 45 millimeters. The length on original diagram is 12 millimeters. I can reduce this fraction to the lowest term. Both of these two numbers has 3. So I will divide both of these two numbers by 3. I will get 15/4. You can keep this fraction as the scale factor. You also can change this fraction to the decimal for the scale factor. So I can say the scale factor is 15/4 or 3.75. So let's look at example 3. In example 3, we need to use a scale factor to determine the new dimensions. We all know the scale factor is a ratio, which is equal to the ratio of the length on the scale diagram to the length on the original diagram. But sometimes we need to determine the length on the scale diagram based on the given scale factor and the length on the original diagram. So if I want to find the scale factor dimensions, I need to multiply the corresponding length on the original diagram by the scale factor. So here is the transformed formula. I change the quotient, which is a ratio form, to the multiplication form. So the scale factor times the length on the original diagram equals the length on the scale diagram. So here is a photo of Einstein. The original dimensions of the photo are 9 centimeters by 6 centimeters. Right now, I want to enlarge the photo by the scale factor of 3.5. Let's find the dimensions of the enlargement. If we want to find the dimensions of the enlargement, which is the scale diagram, I need to multiply each dimension by the scale factor. So the length of enlargement on the scale diagram equals the scale factor times the original corresponding length. So it's 3.5 times 9 centimeters. I will get the new length in the scale diagram is 31.5 centimeters. Likewise, the width of enlargement on the scale diagram equals the scale factor times the original corresponding width equals 3.5 times 6 centimeters. This one is 21 centimeters. So right now, the new dimensions of the enlargement are 31.5 centimeters by 21 centimeters. Let's look at example 4. Draw a scale diagram that is enlargement. On the grid, draw a scale diagram of this L-shaped metal bracket using a scale factor 1.5. Let's determine the length of each line segment in the scale diagram by multiplying each length on the original diagram by 1.5 first. Find the new dimensions. 1.5 times this 3. This 3 is enlarged by 1.5, so the new length for this vertical segment will be 4.5 centimeters. And this one is also 3 centimeters. The new dimension of this horizontal segment will be 4.5 centimeters as well. 1.5 times 2, which is the side length here. This one will be enlarged by 1.5, so the new dimension will be 3 centimeters. This one will produce a new dimension 3 centimeters as well. The original dimension of this one is 1 centimeter. After this one is enlarged by 1.5, the new dimension will be 1.5 centimeters. So both of these two blue segments will become 1.5 centimeters. So let's draw the scale diagram. This one becomes 4.5. Let's start from here. Get 4.5. So this one will be also 4.5. I will do 4.5 again. So this one will become 1.5. So let's find 1.5. This one will become 3 centimeters. So let's get 3 centimeters. This one will also be 3 centimeters. So this last one must be 1.5 centimeters again. So this one is the scale diagram of this original diagram. And we also can see this one is an enlargement of the original diagram. Example 5. Let's use both of the ratio form for the scale factor and the product form for the length on the scale diagram to complete this table. I know the length of original and the scale factor. If I want to find the length of scale diagram, I need to use scale factor 3 times 15 centimeters equals 45 centimeters. The second row has exactly the same given conditions. So the length of original is 0.8 centimeter. The scale factor is 15 over 4. I will use the scale factor 15 over 4 times 0.8 centimeter. So this one will give me 3 centimeters as the new length in the scale diagram. If I know the length of original, the length of the scale diagram, how can I find the scale factor? I use the ratio form. I will use 75 centimeters over 2.5 centimeters. I will reduce centimeters and get the numerical value 30. This is 30 is the scale factor. In the last one, I'm given the length of scale diagram and the scale factor. How can I find the length of original one? If I want to find the length of original one, I will use the length of the scale diagram, which is 45 millimeters, divided by the scale factor, 3.75. So this length of original should be 12 millimeters.